by Guilherme Sipahi from the University of São Paulo.
Okay, thank you very much. It's a pleasure to be here. I will talk a little bit about 2D materials, the Dichalcogenides, but in a different way. So I'm working with these guys that are material science guys. So their interest is in how we exfoliate material. So what we did here, so it's work for Carlos Bastos, my student, and Rafael Bess and Juarez that are at chemistry department in University of São Paulo that are just material science guys. Okay, I will not talk about that, but then material has lots of applications, especially on this material science way of thinking, not exactly spintronics or so on, but several ones, photonic device, electronic device, biosensors, storage, and Dichalcogenides became something important in general fields. So the idea on this work is to study a class of them and try to find in which phase they crystallize, which one is the most stable, if there are some metastable ones, and then if you can exfoliate them from a bulk in order to get to work with them. Okay, so the goals were that, discover stable and metastable phase that can be synthesized, identify structural, energetic, and electronic properties of bulk TMDs, identify which materials are easily exfoliated in a monolayer, and then classify them and the stables and metastable phases, and either if they are insulator, semiconductor, metal, or semimetal. Okay, we did that for this a class of materials that comprise three columns of chalcogenides, and then transitional metals, and then the three chalcogenides most commonly used. So sulfur, selenide, and telluride, from titanium to chromium, from titanium to hafnium, and tungstenium. Okay, so what we did, we ran 85 different structures, okay, in just three different phases, 2H, 1T, and 1TG. What we have to do here is to okay. We have to look, and as these are very close in order in arrangement, atomic arrangement, they can exchange from one to the other, and the energies are bonding energies are very small between them. So we have to study that, and from 2H, 1T, and 1TG, that's a distortion on that through periodization usually. Okay, so we went to GFT, so we are using GFT through VASP. We use the PB functional to find the equilibrium volume, relative energy, and last constants. But to get DOS and band structure, we use this much more accurate hybrid functional, much more expensive also, HSC06, that can be very close to the gap. It can transform our numbers in numbers that are almost accepted as a gap. And we also use van der Waals cohesion. We may have to use because these are van der Waals materials. Okay, so our results for relative energy are presented here. So we have a class of S2, SC2, selenides, sulfides, and tellurides. And as is when we started, we thought that TG would be the most stable phase in this, and these results shows that that's not always. Okay. By the way, sometimes the phases have very small difference among them, as in this vanadium, niobium, and tantalum places. Sometimes they have very big difference on energies, so we can say that this 2H is much more stable in this case. So what we have is, for this class of materials, we have 1G as the most, 1Tg as the most stable phase from Gs, we cannot say. And on Gs, the 2H. So we have a trend on Gs on the three materials. Okay. Also in here, you can say if they are antiferromagnet or ferromagnet or just metal or semiconductor. Okay. I will present these results later also, more in a more. Okay. So what we say for TE materials, the most stable phase is usually 1Tg with small exceptions. Okay. And this is the, for exfoliation, this is the most important result we have. Running all of them, we could find a clear trend on relating Bader charge to exfoliation energy. Okay, so what's Bader charge? Bader charge is a way, it's something that you use to determine positions of atoms based on the electron density. Okay, so you calculate the density of electrons on the system, and you find the place of the atoms by this density and saying, okay, there's one atom here, there's one atom here, this is the limit. If you calculate this, you actually measure the energy difference, the electric field among two different layers. And what we found here is that this difference is fundamental on describing it. Okay, so you can see a clear trend here for 2H and also for 1T. Sometimes in very complicated systems, sometimes they are ferromagnetic or not, or there are other big atoms or so, you find some materials out of, but most of them follow this curve. Okay, so we found that exfoliation energy has a linear behavior for this, and we can find also lots of materials with a good, very easy to exfoliate from that. We can look at this part of our graphic to see these materials are easily exfoliated. Okay. We also went to calculate the lattice parameters, and then they are mostly monotonic. Some materials, the same ones that we cannot relate to Bader, lose from that. So this is one parameter A, this is C parameter, so this is plane, and this is out of plane. And in this, we see according the size of the number of chalcogen atoms. This is according to the parameters according to the transition metal period. So we are going on this line on the column, and also on this. These are the trends. Exception for very small ones are pretty consistent. So they are pretty regular in some sense. Okay. We also calculate the last constants, and also you can extrapolate very easily then. They perform the same range, except for here, okay, and for here. So again, we can have a single model that shows this, and then you can extract this from our table. Now, calculating the band structure, what we have here are three different materials, okay? Zirconium selenide, niobium selenide, molybdenum selenide. We can see three situations: a semimetal, a metal, and a semiconductor. You can see that, and the most important thing that we see here is that are the g orbitals that play this role. If depending on how the g orbital is there, you have some density of states that detach itself. So this trend goes from here to there, and then what I can say about them, if you are looking for a metal or some metal or something like that in these materials, you should look for the g orbital. Is it deep inside? No problem. We can bring, if it's very up, you can have a semiconductor. But if it's at the same place as the other, you have a clearer semimetal. Okay, and this is a table that shows our classification. So in this we have all the materials, and we have the selenides, the sulfides, selenides, and tellurides, and here we have all the materials that it composed in each of their phases. So if you read here, you have metals, or semimetals, or semiconductor. In the semiconductor, we put the gap, the value of energy gap, probably close to experiment due to the fact that we are using HSC06. And we also say that some of the materials cannot be stabilized on this 1T phase that occurs through pure distortion on the 1T. So that almost summarized the electronic properties of these materials. Okay? And then this is what I would like to talk to you about Dichalcogenides. I was talking a little bit more about that, but I saw some talks here, and I had this idea to introduce another team. So if someone can like to ask something about that, please do so, because I will change topics. Now, I will try to talk to you a little bit, almost the same moment, about this, that is a material that's a 3D material, but is Hamiltonian, is probably very close to, sorry. Okay. I'm having trouble with my mouse. I have to put this on the presentation side. Oh. Let's see if I succeed. I was going to try this. Eu ia tentar fazer isso na hora do intervalo, mas você me falou para fazer antes. Checar se está tudo em ordem. Não foi. Mais uma. Isso aqui. Okay. Now, let me find the... So, no, this is, I just did the, now we go. Buttons are very close, one to the other. Okay, this is a 3D structure. Okay, I'm sorry about talking about 3D structure, but what may be important for you here is that 3D structures look just like bilayer graphene. So if we go on this structure, we can look at the Hamiltonian that we can extract from BHZ model. It's just like the bilayer graphene. Okay, so I will try to do a presentation on this structure that can be related through the Hamiltonian, and then I will acknowledge my colleagues here. Thiago de Campos did most of the work, was my PhD student, moved to work with Igor in Buffalo, and now is back to Brazil, out of the academy. Marcelo Alejandro Tolosa Sandoval is presently at the Universidade Federal da Bahia as a postdoc, and Léo Diago Cisneros is from Cuba, helped us, suggested the material, mostly. Okay, this material, we will study this kind of files. This is a topological insulator, usually, done by stacking different materials in an order and having Rashba to break inversion symmetry here. So this has been used since, I don't know, the 90s because of the break of Rashba symmetry, and has been found to be a topological insulator some time ago, a little bit. And this guy is very well known. The idea here is, as this kind of systems use Rashba symmetry to introduce Rashba splitting and to get to the topological insulators, we unbreak the inversion symmetry. So we put a second well on the side that turns the system again symmetric. So then, applying a small electric field, I can break again the symmetry and turn from a regular material to a topological insulator. At least that was what we thought about. Okay, so let's just advertise a little bit our model. Usually when we are studying this, you use a BSD-like model, so you have effective Hamiltonian, then you confine, and you use extract from reality, use this, confine the other direction with a small Hamiltonian again, and then you have, you see things like that. So you see one-dimensional wave functions and so on. We are using a full 3D K.P model, so we model everything on together, and what we see like that, usually you see like that in BHC-like model, we see as this is our density, is 2D density, so you grow and it goes back. If I had some color, I would see this kind of movement there. Okay, what's important for starting to know here is that on green, this is a regular material, this crosses to a situation where you invert the gap, and then in red, the gap is inverted. Okay? And we have two situations. We have a situation where we have two holes in the side and electrons on here. You may use the BHZ model and say these are holes in BHZ, electrons in BHZ here, or we'll have holes in BHZ and electrons here. And as electrons may interact with light holes, these systems are fundamentally different. How are they different? Like that. This is the one where holes do not interact with electrons, so they could not hybridize with states here and hybridize again, so they are confined to these layers and electron confined to here. And when you go from the situation where you have a regular material, you are very close to band crossing, to band inversion, and when we invert the band, the situation we find is this one, okay? You pin one hole that represents states here with another hole that represents states there, and you have in between the electron passing by. So you pin it, you close the gap, and you never reopen until you break the symmetry. In the other system, that situation is slightly different. So you go there, and you start interacting, and you open an effective gas that may be inside the valence band in a general way. So you have this K. In this K, you have a gap, but this is inside the DOS. The DOS is full on. But you can still distinguish between states. There will be edge states here, surface edge states here, and they will be different from the bulk states. Yes?
So do you actually, is this a self-consistent calculation?
No, there's no charge here. Just in this kind of systems, as these are wells, you can inject or extract charge. This is the first calculation. We didn't use charge yet.
But they are in. But where is the chemical potential? Somewhere.
You may move the chemical potential, but if I may move the chemical potential, I will have to do self-consistency that I did not yet.
Which may change completely.
Probably,
things.
but not this. I don't believe this will be changed
Why
that
not?
much. Why not? Because there is a symmetry relation among them that will not be broken by it. I don't believe that this will change much. Probably what we'll have here is a difference on the, it should change a little bit the effective mass close, but not really the bottom of the way these transitions behave.
It will certainly depend on how you put the doping and because the electron hole interaction there. It's going to be very strong. That's known in this kind of system, right?
Yeah, yeah, of course. But there's a symmetry well established here that may prevent they from changing character in this.
What kind of symmetry you're talking about? I'm talking about this.
I just put the Hamiltonian there, and I look for BHZ-like model. I try to find them, and I think they are stable on a very high range. Okay, but I didn't do. I cannot answer your question because I didn't do.
Right.
Okay. Okay. So now is the behavior under the electric field. And the behavior under the electric field shows the symmetry break here. Okay, you see like this spaghetti and these strange things here. You always have a gap there. Okay, and this is the second system. It's much more well behaved, so you can see and stays there. Okay, so Rashba electric field gives Rashba splitting and then breaks the symmetry. Okay, so again, what I will show now is the dense, the wave functions on the system. I will show later. These are the three layers. So you have the wave functions on gallium antimonide, indium arsenide, gallium antimonide, and so on. So remember this because the next slides will need for you to understand what layers are. Okay, so these are three conditions on one of my systems. This is the system that has electrons on the side and holes on the side and electrons in between. You can slightly see here that you have something that looks like the a Dirac cone, but does not express itself. But you can see the band structure going here. Every time you have anti-crossing, you see the band structures goes again, linear and so on. And what you see here in the band, as the wave function is that is at the surface, very far away. When we, this is the dimension, the big dimension there. You can see the wave functions at the border, the edge, okay, between the edge of the material, and but you do not see the same wave function going from side to side. When you apply electric field, you see that you have edges, but then they are symmetrically placed, so k and minus k, and that's the wave function that arises from the Dirac form, the Dirac cone. This is helical also, but it's not coming from, I cannot say they are topologically protected because I don't have the same feature. And then we increase and then if we go further on the band structure, it starts to becoming a bulk state. And you can see clearly here, these are bulk states, they are delocalized going on all the layers. So you can see that. So the transition from edge state to bulk layer may be seen here, here, and then there. That's the usual way of doing. It starts having nodes that you cannot, nodes that you can clearly see and became a bulk system. And this is the, okay. And this third one is the different one. So we have the Dirac cone, and it's embedded. It's inside the DOS, the density of states. So valence band DOS come from here down. You have a gap, but you have valence band DOS, and the Dirac cone is buried inside. It's buried inside, but gives signatures of edge states, like you can see here. When you go there, you start seeing a bulk-like state. So when you are here, you start seeing a bulk-like state. Here, it's completely different from this perspective. Okay. So now I will go into the other. I passed by this on the end. So here is regular material. Here is regular material. These are the sizes of the wells. And this region is the region where the band cross. I should have done this from the other material. I skipped it for some reason. And this is the a K. This is the 2G, so K varies, and then you have just an indetermination on K. It's showing here. Okay, this is a material where the gap is always defined. A system where the gap is always defined. And that's the same behavior as before. So when you see different Ks, this is hole, this is electrons, so they are at the interface. When you apply the electric field, this is defined as the signature for the others, for edge states like we saw. And then when you grow, increase the magnetic field, you see the Dirac cone embedding then and again inside the DOS. And in this case, the gap is closed by the electric field.
So, just to understand, this is probability density what you have in that case of the states?
Yeah.
And so...
so they have different cases on the system. So
yeah, but in the, you show this, the edge is along the y direction?
Yeah.
And you show some edge state, but why you have only on one side?
This is probably because the symmetry is not broken. They are free to go wherever they go. You don't have Harashba there.
But this time
you will still have some interface states. They are not Rash. They don't have Rashman to break the symmetry and to define the topological ones in the sense we are looking for.
But you have time reversal symmetry. You have
but I have 4 states. I have 4 states, so they may combine. I have more states. I double the number of states that I'm looking for. Maybe yeah, the symmetry is along Z. Yeah.
So C is which direction is C? Which direction is C? So the plane of the is X, Y, and C is the perpendicular?
Z is the perpendicular one.
Oh, I see.
Okay. Okay. See.
So, can you tell us exactly in the band structure where are these states? What's the relation between this set of states and their energy?
These lines are the states.
I guess she's referring to the chemical potential. Yeah. No?
Usually the chemical potential is just in the middle. It's at there, because I don't have charge, I just occupy. So the chemical potential is just at the Dirac point.
Because I see some bulk states.
Yeah.
And these are probably from
here.
Far below in the...
From far below, yeah.
But the ones that are localized, like
in this case, the localized ones are here in this energy. The ones that are bulk are in this energy here. Okay, so these lines define the K and the energy you can follow here. So these two are not in the same energy, but these are pretty much the same energy.
Boundary correspondence, right? Bulk boundary correspondence is not showing up somehow. Because you have states, it's still not clear whether the localization is along Z or Y. Because if it's
the
along
localization
Y,
is Y, Z is here. Localization
then there is no
is here.
bulk boundary correspondence.
Yeah, and then you have the other one. This goes, the third direction is here. And this is probably, I didn't do the calculation, but the currents must be in this direction, going out of lane.
Yeah, it's very intriguing.
Okay. So I would like to thank you all for listening to this very different way of thinking. Okay.
We have more specific questions. If not, we can maybe continue with the discussion during the coffee break. And so we're back here, should be back here in 20 minutes.